In this lesson, we're going to talk about two common continuous distributions. The first is the uniform distribution over an interval AB. So x is uniform over the interval AB if it has PDF f of x equals 1 over b minus a for x between a and b, and f of x equals 0 otherwise. If x is continuous and uniform, then the expected value of x is a plus b over 2. So it's just the middle of the interval. And here we've got an interval from a to b, and f of x is just 1 over b minus a. So in other words, it's 1 over the length of the interval. And what we're saying is that the mean is right in the middle. So that's the average value. You can find it by direct computation. So the expected value of x is the integral from negative infinity to infinity of x f of x dx, which is only non-zero from a to b. So it's the integral from a to b of x over b minus a dx. And that's x squared over 2, and the denominator still has b minus a. It's evaluated from a to b. So it's b squared minus a squared divided by 2b minus a. And factoring that, this b minus a is b squared minus a squared is b minus a times a plus b, which gives you the a plus b over 2, because you can cancel a b minus a with a b minus a. The variance of a uniform random variable over an interval ab is b minus a squared over 12. So to find the variance, we're going to first compute the expected value of x squared. So we're looking at the integral from negative infinity to infinity of x squared f of x dx. And again, f of x is only non-zero on ab. So we're looking at the integral from a to b of x squared divided by b minus a dx. So now we get x cubed over 3 times b minus a evaluated from a to b, which is b cubed minus a cubed over 3b minus a. And here we're going to use the fact that b cubed minus a cubed is equal to b minus a times a squared plus ab plus b squared. And so the b minus a's cancel once again, and we have a squared plus ab plus b squared. So using the formula for variance, the variance is the expected value of x squared minus the expected value of x quantity squared, or a squared plus ab plus b squared over 3 minus a plus b over 2 squared. And essentially all of this is just algebra. So we square this term out and then get a common denominator of 12. Then since we have a common denominator, we can combine all the terms in the numerators, and that gives us a squared minus 2ab plus b squared, which factors to b minus a quantity squared. So for example, if x is a random variable with PDF 1/2 over the interval from 1/2 to 2.5, then the average value is 1.5 and the variance is 1/3. And if we were to graph this, here's maybe x is 0, so we go to 1/2 or 0.5, and so 5 halves or 2.5, and it has height 1/2. That's because this is length 2, so that just gives us a box that has area 1. That's 2 across and 1/2 high. The mean is right in the middle, so it's 1.5 or 3 halves, and the variance is 1/3. The other random variable we want to look at is the exponential random variable, and we say x has the exponential distribution with parameter lambda bigger than 0 if the PDF of x is f of x equals lambda e to the minus lambda x for x bigger than 0, and f of x equals 0 otherwise, or in other words, 0 for x less than or equal to 0. If x is exponential with parameter lambda, the expected value of x is e of x equals 1 over lambda. And this is once again solved by just direct computation. So the expected value of x is, in this case, the integral from 0 to infinity of x times lambda e to the minus lambda x. Then you can use integration by parts to get x e to the minus lambda x evaluated from 0 to infinity, plus the integral from 0 to infinity of e to the minus lambda x dx. This is just 0, because when you plug in infinity, the e to the minus lambda x goes to 0 faster than x goes to infinity, so it tends to 0. And then when you plug in x equals 0, you get 0 times 1, which is 0. So we only have this integral remaining, and that's e to the minus lambda x over negative lambda, evaluated from 0 to infinity. And once again, when you plug in infinity, this goes to 0. And then when you subtract the value where x equals 0, you get 1 over lambda. So this is the expected value. And to find the variance, we once again compute the expected value of x squared. So we're looking at the integral from negative infinity to infinity of x squared f of x dx, or in other words, the integral from 0 to infinity of lambda x squared e to the minus lambda x dx, once we plug in the PDF. And this is again solved by integration by parts. So you integrate by parts, and this is 0, and you're just left with this. Then you can integrate this one by parts, and you get something again that's 0, and you're finally left with something that is non-zero that you can just evaluate without integrating by parts. So you get 2 times the integral from 0 to infinity e to the minus lambda x over lambda dx. And this is negative 2 e to the minus lambda x over lambda squared, evaluated from 0 to infinity. As x goes to infinity, you get 0, so you get a positive 2 over lambda squared, since whenever we plug in 0, this is just 1. So you get 2 over lambda squared. Now using the formula e of x squared minus e of x quantity squared, we get 2 over lambda squared minus 1 over lambda squared, since that's the expected value of x squared. And when you subtract those, you get 1 over lambda squared. So the variance is 1 over lambda squared. The mean is just 1 over lambda. So if x is exponential with parameter lambda and t is bigger than 0, the probability x is bigger than t is e to the minus lambda t. And in other words, the CDF is f of t equals 1 minus e to the minus lambda t. I guess it should be pointed out here, this is only for t bigger than 0. If t is less than or equal to 0, then f of t is just 0. So it's pretty easy to compute the probability x is bigger than t. It's the integral from t to infinity of lambda e to the minus lambda x. You bring down a negative lambda, and the lambdas cancel, so you get minus e to the minus lambda x from t to infinity. As x goes to infinity, this vanishes, and so you're just left with e to the minus lambda t. And then the CDF is 1 minus that. The probability x is less than or equal to t is 1 minus the probability is bigger than t, which is 1 minus e to the minus lambda t. And so, for example, if x is a random variable with PDF f of x equals 4e to the minus 4x for x bigger than 0, then it's exponential with parameter lambda equals 4, and the mean is 1 over 4, and the variance is 1 over 4 squared, or 1 over 16. So a common application of an exponential distribution is the time until an event occurs. So for example, if there's a certain part of machinery that's estimated to break down roughly every 2 years, given a new machine, how likely is it that the machine will last more than 3 years? So without any other information, our best guess might be that the time at which the machine breaks down is going to be exponentially distributed. And since the expected time is 2 years, the parameter is 1 over 2. Because 1 over lambda, or 1 over 1/2, would be 2. So the probability it lasts more than 3 years is the probability that the time t is bigger than 3, which is just e to the minus 3 times lambda, or in this case, e to the minus 3 over 2, since lambda is 1/2, which is roughly 0.223, or there's about a 22% chance that the machine would last 3 years. There's an interesting property of exponential random variables called the memoryless property. So if t is an exponential random variable, the memoryless property states that the probability t is bigger than little t plus little s, given that t is bigger than little t, not p. This is equal to the probability t is bigger than little s. So in other words, the probability that t lasts 4 years, given that it's already lasted let's say 1 year, is equal to the probability that t lasts just 3 more years. So you can actually get rid of the conditioning and just subtract this, like 4 minus 1. So we'd add a t plus s. Given it's bigger than t, you can subtract the t off and just find the probability that it's bigger than s. And this can be shown just algebraically. So the probability t is bigger than t plus s, given it's bigger than t, is the probability that t is bigger than t plus s and it's bigger than s, divided by the probability it's bigger than t. Well, if t is bigger than t plus s and it's bigger than s, that's the same thing as just saying it's bigger than t plus s. So this is the probability t is bigger than t plus s divided by the probability is bigger than t. Then we can use the fact that we've already evaluated these probabilities. So the probability is bigger than t plus s is e to the minus lambda t minus lambda s, and the probability it's bigger than t is e to the minus lambda t. Then these two probabilities cancel, or these two exponentials cancel, sorry, so that leaves us with an e to the minus lambda s, which is the probability that t is bigger than s. So in a sense it's memoryless, or it forgets the time that it's already been given. So if you're given that it's lasted t time, you're questioning what's the probability it's going to last s more time. It says the probability that would have lasted s time from the beginning, and it forgets that this has already been t amount of time.